This is one of a series of revision lectures produced by the Further Mathematics Support Programme for A-Level Mathematics. In this lecture we're going to be looking at the Edexcel Decision Mathematics 1 specification, and in particular the topic of critical path analysis. Now, the specification says that you need to be able to model a project of an activity network. So given a network, then produce a precedence table, i.e. looking at those activities which take precedence over another, which ones must be completed before a particular before the next one can be started. Or the other way around, given a precedence table, draw an activity network. The algorithm for critical path that you need to use is the idea of looking at a forward pass. So we move through the network from the earliest time to the end to find what are called the early event times. These are in fact, it's the longest path from the start to the particular event that you're looking at. The early event time, that's the earliest we can get there, so that everything that needs to be completed to that point can be completed. We then do the reverse of that, so a reverse pass, which starts at the end, as it were. So we go to the latest point and move back, looking at what are called the late event times. And this is just done by subtraction. So this would be the 8 late events. So that each node on the network is an event which has an early time and a late time. And it's connected by an arc which represents the activity to the next event, which would be J, which has its own associated early time and late time. So the activity, I'll call it IJ, and that will have some duration to show how long that activity takes. The float that's referred to, the float time is equal to, well, actually defined as the float IJ is equal to the latest time that we can be at activity J minus the earliest time at the previous activity minus the duration of the activity. So that we're looking at, to get a different colour on my pen to do this, we're looking at this time here minus this one and minus the duration. The float time, if it has any particular value, allows some slack within the system. It means that the activity, if it exists, the float allows the activity to be delayed a little bit without affecting the end of the project itself. If, however, the float is equal to 0, then we say that the activity is critical. It's what's referred to as a critical activity. So if the float IJ is equal to 0, then the activity from I to J is termed a critical activity, and it must be done on time, otherwise there will be delay in the end of the project. In activity networks, then there are some activities which have to be put in which don't actually involve any work being done. They're what are referred to as dummy activities. Two reasons why a dummy activity might appear. One is simply that we're not allowed to have two activities joined by, two events, I beg your pardon, I and j, joined by two different activities. So this is just simply not allowed. So we have to put in this, a new event, to show this precedence. And what we're saying then is that we can go from I to j with our two different activities, but then we want to link those two together. The second type of dummy activity is one where we have two events which are joined by an activity, let's call it P, and leading on from there we've got another activity R, and then separately we want to show a different activity Q, which has S leading on from it, but we want also to have R dependent on Q. So if R depends on P and Q, but S only depends on Q, then we need to show that extra dependency by a dummy activity going between event L and J. So two reasons why dummy activities might appear on a flowchart. The final thing then is, once we've done all of this work, is to look at the idea of a Gantt or cascade chart, and this shows the number of workers that are required at any particular time. And therefore, once we've done this diagram, this is like a histogram on a timeline, then we can use that to schedule the activity. So where there's some slack, we might be asked to move some activities so that we can look at the number of workers involved to complete the project. Okay, hopefully all of those points will be illustrated by the exam question that I'm about to look at. Well, this question was from the June 2011 paper, as it says. You'll see it's quite a long question, but we'll just read through it. First of all, we've got a project which is modelled by the activity network shown, it says, and the activity is represented by the arcs. The numbers in the brackets are the time in days to complete each activity, and each activity requires one worker. The project is completed in the shortest possible time. So the first thing we're asked to do is to complete a precedence table, which is in the answer book. We'll look at that in a second. It's on the next slide. And then to complete diagram 1 to show early event times and late event times. Once we've done that, we can find the critical activities. And then finally, well, not quite finally, I beg your pardon, but the final part of the actual algorithm is to use what we know so far to draw a cascade or Gantt chart. Then the final part of the question is a sort of more searching idea to see if you understand what is going on your Gantt chart. And it says, we have to explain why it is not possible to complete the project with just 3 workers in the minimum amount of time. So obviously that part of the question we can't actually really understand fully what's going on here until we've actually got the Gantt chart in front of us. But otherwise, this is a fairly standard critical path analysis question, where we've got a precedence table to complete, the diagram of early and late event times, so that's you doing the forward pass and the reverse pass, finding the critical activities, and then drawing a Gantt chart. Well, here's a repeat of the picture of the network that we had in the question, and the precedence table referred to on which would be in the answer book is below it. So what we need to do is to, as it says, complete the parts of this precedence table which have been left blank. So the first one to look at is C, and then just looking at the diagram here, what we need to do is to look at C and which activities come immediately before it. So moving back to event 2 there, we can see that the activities there are obviously A, but also we must remember that there's a dummy activity here which shows that C also depends on B being complete. So within the table then we need to write in for C that A and B are preceding it. The next one which is missing from the table is E. So going up to the top, and we have a similar thing for E, don't we, that it's basically coming from event 2, so it would be the same precedence there, and that we've got A and B. H is the next one to look at. Well, H is coming from event 4. So what comes into that? Well, D does, and C. So putting those onto the diagram for H, C and D. I comes from event 5. And if we look at that one, we've got E, but we've also got this dummy activity in here. So we also need to then look back at where that's coming from. It's coming from event 4. So I depends not only on E, but also on C and D. So for I can write in C, D and E. Well, J is coming from exactly the same point here, from 5, so it must have the same precedence as I did. So that also will be C, D and E. We're nearly finished now. K is in here. If we look at the precedence for K, we're looking at event 6. And that is I, H and F. So putting those into alphabetical order, it doesn't actually matter which order you put them in, as long as we get them all in there. F, H and I. And finally, looking at L, which has got G, but also again another dummy coming in here, so we have F, H and I coming from event 6, in the same as K. So L depends on all of F, G, H and I. So that's the precedence table complete. The marking of that before I move on to the next stage, basically it depends on how much of it you get correct. So the marking was given as B1, B1 and B1. So 3 marks available. The first B mark was for 2 of the boxes correct. The second one for 4 correct, and the third one for all correct. Moving on now to the second diagram, the second part of the question asks us to mark in early event times and late event times onto this network. It's worth just checking on the key to make sure that we get them the right way around. The early event time is once in the upper box and the late event time in the lower one. So we're going to begin right back at the start of the activity here, and of course that gets underway at 0 time. Now the idea is from there that we move through the network and finding the longest path first of all to each point. Now if we just look at A, that has got a duration of 4. However, remember that we've got this dummy in here, so we've got to look not just at the 4 but also what's going on with B. And you can see that B's of length 7, so that means that actually the earliest time that we can reach that event is not 4 but it's 7. And that's true also of the event at the end of B there. Now if we work forward from there, looking at C, what happens to, sorry, I beg your pardon, not C, but what happens to this event here, we can see that from the 7 that we've put in at the top, we've got C as duration 4, that gives you 11, but from the 7 at the bottom we've got D with duration 5, so in total that's 12, so the earliest that we can reach that point is 12. Just continuing, moving forward in that way. Then to this one here, I'll just move that up a little bit, there we go. That one there, we've got 12 with a dummy in from the event that we've just been looking at, and then from the 7 to the left there, plus 2 is 9. So again, the earliest that we can reach that point is 12. At this one here I've indicated we've got quite a lot of checking to do now. So first of all, from the 7 we can add on 5 to that to give 12. From the 12 at the top, following on from E, we've got I as duration 3, that gives you 15. And from the left, 12 plus H of 4 gives 16. So the largest of those is 16. That continues through to the bottom point there where we've got 16 because of the dummy in here. And then for the final point, we need to just check through and say that at this point we have 16 plus 6, which is 22, 16 plus k of 5, which is 21, or 12 plus 10 is 22. So two of them there giving you a value of 22. To work the reverse path and calculating the late event times, we start at the end of the network with the 22, and this time we're subtracting. We're looking really for the shortest path this time because we're looking at the late time that we can be at a particular point. So now what we're going to do is to take the 22 and subtract. So 22 minus 6 is 16. And that gives us our value here of 16. (22 minus 5 is 17, but we've got to look at the 16 that's here, and so therefore the the latest that we can be there is not 17 but it's 16. Carrying on up to the top of the diagram, this point here, working back, 22 minus 10 for J is 12, 16 minus 3 is 13, so the smallest of those is 12. And very quickly then, just finishing off the rest of the diagram the similar way, the dummy here and the 16 actually minus a 4 both produce a value of 12. this one here, actually we need to go, I beg your pardon, to the one at the top first. 12 take away 2 for E is 10, but 12 take away 4 for C is equal to 8. We needed that 8 because it links via a dummy to the bottom one here, so the 16 minus the 4 would give 12. That's looking at the path for G, but the dummy in there means that we've got 8 in this position here as well. And finally we get back to our I beg your pardon, it should be 7, the smallest of those. Yeah, so what I did there was make a very easily done mistake, which is not to check every single path. So we need to look at the 12 as well. 12 minus 5 is 7, and the 16 minus 5 is 11. So the smallest one is not actually 8, so let me just correct that and put those right. The top one, the early time was 7, and the late time is also 7. And finally, to finish off, we get the 0 at the end. So that's completed our network diagram of early and late times. The next part of the question asks us to look for critical activities. Now, what I would say to you is that to do that, it's worth looking at those events where the early time and the late times are the same. There's quite a lot of them in this particular question, because activities which join these critical events may be critical activities. However, we have to be careful. We've got to look at the late time of one event, the second event, minus the early time of the first event, minus the duration. So remember that I wrote down earlier that the float time ij was equal to the late time at j, that's the second event, minus the early time at I, the first event, minus the duration ij. So what we're looking for is those activities where that is equal to 0. So the one I've indicated here, j, that is definitely true. We've got 22 minus the 12 minus 10 is equal to 0. So that activity is a critical activity. Now what I'm going to do is to indicate that by scribble on that line there, and we can go through the diagram in similar ways. Now just to illustrate what I'm saying a bit further, if we look at K, although that joins together two critical events, the 16 and the 22 there, 22 minus 5 is 17, so K is not a critical activity. However, L is. So this one here, because 22 minus 16 minus 6 is equal to 0. Continuing through, H is critical, and also D and also B. So those are the critical activities. The critical path, although we're not asked for a critical path in this particular question, is B, D, H, L. And also we have this other critical activity, so another critical path which goes B, D, and then via the dummy to give us J. So all of those are critical activities. We're asked to list them. They are B, D, H, J, and L. The marking for this was an M1 A1 for the early event times and a similar M1 A1 for the late event times. So the method marks just some idea that you have to convey some idea that you're doing the right process, that the numbers are generally increasing as you go from left to right, and then you're looking at subtraction afterwards. There's a method mark and an accuracy mark for the critical activities. The next part of the question asks for a cascade diagram. This is basically a histogram showing the activities on a timeline. So here's our timeline at the top. It goes up to 24, notice. Now we're only going to need to go up to 22, of course, but they're not going to give that away in the question, so do be aware of that. We're not going to use the whole of this timeline. But what we do, we put on a bar indicating each activity at the correct length. The convention is to start off with the critical path, which will be a continuous bar all the way from 0 up to 22, and then divide that into the activities. The first one is B, which goes up to 7, followed by D, which is length 5, so that comes up to 12, then H of length 4, bringing us to 16, and finally L of length 6. J is also critical, so we can give that its own little box. It must start at 12 and must be finished at 22, and of course its duration is 10 days. The other activities are marked on individually, one at a time, showing normally to the left hand side. So A we're going to put in as a box of size 4, but then it has some float. It has to be finished at latest by time 8. So that's its float indicated there. C can start as early as 7. It's of length 4, so it goes up to 11, but it has a little bit of float time in there, so we're showing that possible movement from C to there. Similarly, E is length 2. It can start at 7, and it likewise must be finished by 12. F is another one which starts at 7, or could start at 7 rather. This time it's length 5. And we need to show that it must be finished at latest at time 16. So we look at the diagram. F must finish at 16, which is at that point. Almost there. G can also start at that point. It's time 4. And it is another one which must be finished by time 16. I can start at time 12. It is length 3, and it must be finished by 16 also. And then finally K can start at 16. It's length 5, so it gives us up to 21. But it has that 1 day grace in there, that 1 day float. So there's our Gantt chart drawn up. The marking for that was given as M1 as long as you got at least 9 of those in the correct positions, and 4 of them had some float in there. So there's M1, then an accuracy mark for the critical path, and then a further M1 and A1 if you got past 9 and you got them all correct. So a further method mark. So again, the more you get right within there, the more marks you get. But in total of 4 marks. The final part of the question asks us to consider between 7 and 16 days, so the day 7 and day 16 as indicated on my diagram now, to say why we can't achieve this project with only 3 workers. Now there's a lot going on between 7 and 16, as you can see on the Gantt chart. So there are 2 ways in which we can go about this. One is simply to look at the total number of days work required in that period. So between 7 and 16 we've got DH 4 days of J, and then C, E, F, G and I, all of which need to be completed. And if you add those all up, you get 31 days. That's 31 man days. But with 3 workers, there are only 3 multiplied by 9, which is 27 days available. So therefore it becomes impossible to complete on time. The other way of arguing the same thing is to look at what happens if you have only got 3 workers. Now this involves some adjustment of the diagram, but particularly if you look at time 13, which I'll try and indicate on my diagram now, there, then you can see that H, J and I must be happening on day 13, the 13th day. Now if we do that, we can see therefore, if we move the other arrow in, we can see that there are going to be more than 4 things happening, sorry, more than 3 things happening at this point here. So a similar sort of argument, or sorry, a different type of argument this time, looking at what happens if we had 3 workers, would be to say that on day 13, H, J and I must be happening. But if that happens, we can't actually move F sufficiently to avoid using 4 workers earlier on. The marking for that final part was simply to give 3 marks for the clarity of the explanation. So there were 3 marks, B1, B1 and B1 given for that explanation. That's the end of this particular lecture. Other lectures and information can be found at www.furthermaths.org.uk.